Hello, all of you. My name is Prasanjit, and this is going to be the second of the series of lectures about how to prepare for professional cloud architect certification for Google Cloud. Now, in the previous session, we discussed about the reasons to take the professional cloud architect exam, the prerequisite knowledge, and we also discussed what to and what not to expect from this exam. Before we begin, let me just remind you, this series of lectures are not tutorials. You have good tutorials available in the official Google learning websites as well as other learning platforms. So you can use them to get your theory knowledge. So what is the purpose of these lectures? Here I discuss about the practical applications of various Google Cloud services, how we architect solutions, and stuff like how we scale it in a real world scenario. So with my experience in the industry, I help you be someone who can really apply Google Cloud products to his or her own use case. So that is the reason behind this. And obviously, when you know how to apply Google Cloud, you know how to obviously pass a certification exam. So that becomes very simple after you really understand the tenets of Google Cloud. So what are we covering today? So this is the second in the series of lectures. And today I'm going to cover a brief overview of cloud computing, what it is, and how Google Cloud compares to other clouds, and what are the key differentiators of Google Cloud. And obviously then we'll start discussing about the various components in Google Cloud: compute, storage, database, data analytics, machine learning, stuff like that. So we'll get a bird's eye view of the various components of Google Cloud, and then I'll try to give you a real world example of say a 3-tier application architecture and how it works for a website. And if we were to build this application on Google Cloud, how would that look like? So this is what is going to be the theme of this lecture. So let's get started. Well, if we go by definition, cloud computing is the on-demand availability of computing resources over the internet that offers faster innovation, flexible resources, and economies of scale. Now, we'll come to all these terms later down in the line in our series of lectures. But for now, you can just think of it as on-demand availability of computing services, just like we need electricity for running our appliances. Similarly, if we need compute power, we can use cloud. Some people say cloud is nothing but someone else's computer that you're renting out and using. Now, before we go on deep into the course, let me just tell you certain terms that I might be using in these lectures. So one is public cloud. So it's simple, as the name suggests. Public cloud is the cloud services for the public. So you can think of large cloud providers like Google Cloud, Amazon Web Services, Microsoft Azure, Alibaba. So these are all public cloud services. When I refer to private cloud, it is something that is developed in-house, specific for a business. So you can think of clouds which are on-premise, which companies build for their own use. Facebook, to a certain extent, uses its own cloud. I think Salesforce also has some amount of its compute power hosted on its private cloud, and lots of other companies do the same. Now, there is another term, hybrid cloud. Well, that is a mixture of a public and a private cloud. Many companies do that, they have their sensitive data, such as financial services data or healthcare data, on their on-premise cloud, and they also use the public cloud for other purposes. Well, there is no rule as such, but nothing written on stone. But this is another paradigm that you might come across, the hybrid cloud. Now, there is another term that's quite common nowadays, that's multi-cloud. There are many companies that might host their services on multiple clouds for various reasons, like for disaster recovery scenarios, for not getting logged in with a certain vendor, and various other business reasons as well, for economies and in the billing patterns, agreements, and different kinds of constraints in different countries and so on. And then there is another cloud which is called a community cloud. Well, that is not very common, but it is kind of a collaborative effort in which infrastructure is shared between several organizations from a specific community with common concerns. So I'll talk about that later in some other lecture. This is a separate topic. I mean, this is not covered in Google Cloud Architect exam. Well, so these are the various kinds of cloud that you might come across. Now let's discuss a bit about Google Cloud and other clouds. What are the key differentiators of Google Cloud and so on? Well, there are various public cloud players, as I mentioned. The biggest one is Amazon Web Services. Then you have Azure, you have Google Cloud, Oracle Cloud, Alibaba Cloud. And these are the major players in the market right now. However, Google Cloud Platform is distinct from all the clouds. And I have been around in the industry for more than 15 years. And I realized that Google Cloud is going to be one of the better clouds in the long run. Why am I saying this is because of many reasons, multiple reasons actually. One of the things that I notice here is the security first approach. Since the pandemic, you might have noticed rapid, maybe 20x or more increase in the number of attacks. Like if you have been into if you're completely into site reliability engineering or managing your servers firsthand, you might have realized the number of attacks that have come in since the pandemic began. Now, those companies who are having a security first approach will survive this down the line. So security and data protection is at the core of Google and all its products. So as a customer of Google Cloud, you will own your data and control how it is used. Google Cloud also has strong internal controls and auditing features that protect customers and do not allow insider access to the data. Google Cloud follows something called zero trust access. So even the internal employees do not have complete access to the data. So with this kind of a approach with security being paramount, it sets Google Cloud apart from the other clouds. And another thing that sets Google apart, GCP apart, is it's an open cloud. Google Cloud offers an open cloud that enables customers to leverage multiple clouds and follow a common development and operations approach to their applications. You might have seen like Kubernetes. Where does this come from? It comes from the Google internal project called Borg, and Kubernetes is open source. Like anyone can modify, build their own Kubernetes and host it. Now Google has a Kubernetes engine as well for you, but the source code is for anyone to work on. So that's the open approach. Google has the Anthos, and it leverages Anthos a lot. Like it says, so what is Anthos? It can unify your public infrastructure and your private infrastructure. You can even, use Anthos as a crux for various multi-cloud offerings. So Google, in that way, encourages open cloud practices. And you might have heard about TensorFlow, again another open source software product from Google and massively popular in the machine learning field. Well, so open source community is the key element of Google's corporate philosophy. So this is going to be a key differentiator. I mean, it already is a key differentiator. Another differentiator is Google's prowess in analytics and artificial intelligence. Well, these are two strong points of Google, and GCP offers fully managed serverless analytics products and services to eliminate the constraints of scale, performance, and costs. Because if you are going to run your own Hadoop or any big data analytics engine, you're going to put a lot of effort into it, because you need people, infrastructure people who have worked in big data, Hadoop infra. You will need the resources, hardware resources to run those massive big data engines. So with Google Cloud, you get these as a service. So you just need your data engineers and data scientists to work on them. They already have these platforms available as a service from Google. So that is another key differentiator, as well as creating dashboards, analyzing the business intelligence from this data is very convenient in Google. We will discuss all this in upcoming lectures. Well, so those are the key differentiators of Google Cloud as compared to other cloud providers out there. Well, now what we are going to do is to understand how Google Cloud can help us. And to do that, I would not take the traditional path of explaining what different Google Cloud services are and how do they help us. Instead, I'll talk about a real-world application architecture. I would talk about, say, a shopping website. Say you have a shopping website and you want to host it. So what are the various components that website would have and how you would make it running? Say, for example, let's estimate for 10,000 users or 1 lakh users. So a pretty mid-sized shopping website. Let's call it shoppingcart.com. So how are we going to host this website? What are the various components that we'll need? And what can we do to scale this to 1 million? So we can discuss that architecture. And then once we get a hold of the various components, I'll explain you how you can replace these components with Google Cloud components. Or if given a choice, how would you move your application to Google Cloud? So by doing this exercise, you will not only understand how a shopping cart website works, but you will also get to understand how to make this website live on Google Cloud. And in the process, you will also understand what are the various components that Google Cloud has. So that is my plan. So we'll start by explaining how shoppingcart.com would work and how would it work on Google Cloud. And in the process, we'll also learn about various services offered by GCP. And this will stay with you forever if you learn this way. All right, so let's say our internet-facing application name is, like the website name is shoppingcart.com, and we have our users from all over the world accessing shoppingcart.com by writing it down in the browsers. So what happens next? As we all know, DNS comes into play. So when we type in shoppingcart.com, this website is actually deployed back in a web server. Now that web server has an IP address. Let's just break it down to the most basic and simple level. So initially, let's say our application is decently popular with minimal functionality, and this one server is enough to handle the traffic. So what happens in that case? Our users will, who access the application at shoppingcart.com, would reach out to the web server by accessing the IP address. So the request that we type in the browser goes to the DNS server, which responds back with the IP address for the server, and this the user's computer will then make connection to our web server using the IP address on port 80, and the website would be visible. Now, if our shopping website grows and say we have some business logic running in there, then we would need some application servers behind the web server to handle some intermediary processes like say authentication about for inventory, different kinds of payment services, reporting services, invoicing, and so on. So all this is handled by our application servers, and there would be multiple if our website is growing and we are scaling. And when we scale and have multiple servers for a particular type, how would we then send the request to all the servers? We put a load balancer in front of them. So that's what you can see in the diagram. You have load balancers when the number of servers are multiple. And where does the data reside now? Because you have multiple application servers, so you need somewhere to store your information. So you have database servers. Now, what kind of databases would you need for a shopping website? So depending upon the type of the data, again, you will have multiple kinds of database server. For example, relational and non-relational databases. I'll come to that in a while. Now, let's say our shoppingcart.com becomes really popular and our servers are not enough and we want to increase our traffic. So as I said, we will have to have load balancers, and we will have auto-scaling groups where we will define that these are the images of our application servers. These are the images of our web servers. So whenever it hits a certain trigger, say the CPU goes to a certain number, say more than 70%, scale the cluster by 1. So that's how we can define certain triggers and rules to scale our clusters. And this when new machines are added, they register themselves under the load balancers, and that's how our traffic flows. So you can see in the diagram, like you have load balancers, and again, some of the load balancers are public facing, and some of the load balancers are internal. So if you're load balancing your application servers, so your web server is calling your application server internally, so you don't need to expose that outside to the outside world. So you would have an internal load balancer in that case. So at this point, you have the capability to scale horizontally. Now, that reminds me of another kind of scaling that's called vertical scaling. For example, if you do not want to scale this way, this is the best way we scale in the cloud, you can also just increase the CPU or memory of your servers. But that happens, say you have one server and it's not working well enough, slowing down, your customers are growing, you say it was 8 gigs memory and say 100 gigs hard disk server, and you have say 8 core CPU, you might scale it to 16 core and say 30 gigs of memory and say 500 gigs of disk. So that kind of scaling, when you have the same server, but you are just increasing the amount of resources on the same hardware, that is called vertical scaling. But this is not a very elegant solution because you have to stop at a certain stage, and not very practical when we are talking about customers upwards of say 1 lakh. Right. So, well, now we have this servers with load balancers and databases and all that. Now, and we have our choice that we want to scale out, and we scale out horizontally. So that's how it works. Now, when we talk of load balancers, there are multiple ways in which you can manage your load balance traffic. For example, you can set up different kinds of algorithms to manage the traffic. For example, you can set up an algorithm called round robin, where the request goes to different app servers in a cyclic manner. So first request goes to server A, second to server B, third to server C, back forth again to server A, and so on. So that is one algorithm. You have other kinds of algorithm like weighted round robin, where you put weights on server. Say I want 70% of traffic to go to server A, the rest 30 to B. So I can balance that way as well. If you have servers of different sizes, maybe you can do that. So that is how the round robin or these kind of load balancing algorithms work. Now, let's come back to the database bit that I was talking about. Now, if you look at this application, our shopping cart, say we have applications that have heavy transaction processing. So we will need to ensure that our transactions are accurate, consistent, isolated, and durable. We all know ACID properties for databases. So in these cases, we use relational databases like MySQL or Postgres. So we use this because data here is stored in tables, structured, and we have all the ACID properties in place. However, there are certain disadvantages as well for these kind of not every use case is applicable for this database, because now the user traffic growing, with the user traffic growing, you will see that when you need a real-time analysis of data, or you need to handle massive amounts of data, say you are generating events, okay? So you want to store those events and then process them later on. So storing these kind of events that is happening. So by events, let me give you an example. Like say, new users, a prospect customers lands up in your website. So his reaching your website is an event. He tries to sign up, that's an event. His sign up fails, that's an event. So you can collect all those information for your analytics to know how many users were driven into the website but could not sign in successfully. So these kind of events are also stored and help immensely for the business. So storing these write data, like these are all write operations from a database perspective. Now, if I start writing it to a relational database, that is costly. So in these cases, what we do, we use NoSQL databases, like for example, Redis, MongoDB, and CouchDB. There are lots of these kind of non-relational databases, and they scale very well horizontally. You have Cassandra, which is a very heavy-duty non-relational database as well, and it has ACID properties. So there are many non-relational which also comply with ACID. So there are different use cases when we use them for storing flat files, non-tabular data. Now, this is different from caching. I'll talk about caching in a bit. So just to get things straight, like this is about flat files, non-relational data, that kind of data which cannot be stored in a table and which is not relational. Like the data can be anything, any event, which might not have relation to other data that is stored in that database. So that is about the different types of database. So you can choose it based on your requirement. Say we have these kind of relational and non-relational databases which our applications connect to. Now, for relational databases, sometimes we might have a heavy read load. So for example, you have some existing customers who are coming in and querying different things. For example, someone has logged in and is searching for a certain product in our shopping website. So these search queries might go back into the database to show us the catalog of different products that he's searching for. Now, these kind of read queries also put the database in a lot of stress. So how do we handle that? With our number of customers growing, we will have more number of queries. So 10x customers, then 100x, 1000x. So we need to scale based on the growth of customers. These kind of queries also scale. So one good way is to use caching. So we can use caching mechanisms such as Redis or Memcached to cache database queries as well. So that is one thing. Now, cache also reminds me of caching at another level, front-end caching. For example, when you go into your shopping website, shoppingcart.com, you would see various products and images of those products in carousels on that page. Say, for example, you search laptop, you see the different carousels with images of laptops. So this image is a media file. So it might have some kind of a resolution, and the better it is, like for example, if someone is watching it on a mobile phone, it has a different resolution. Someone is watching on a HD monitor, so that is having a different resolution. Based on that, these media file sizes change. So if you have these kind of static content, images, video files, media files, so these are to be downloaded from your server to the browser or to the user's system. Now, the longer it takes or the larger the file size, the more time it takes to be downloaded. So it appears that your website is slow. So how to solve this problem? So the user experience might be bad. The user might be frustrated. Well, this website is slow. I don't think it is reliable enough. I would not buy anything from this website because maybe when I'm on the payment screen, this slows down and something goes wrong. So bad experience, customer experience, and you lose customers. So to fix these kind of problems, what we do as architects is use caching, but at a different level, that is called CDN. Now, CDN is nothing but content distribution network. So you have various edge servers all over the places. Google Cloud has edge servers in different locations. So based on the user's location, geolocation, the static files are served from that particular edge cache. So it's faster for the user, so he can quickly download them to his system and use them. So that is what CDN is about. We'll go deep into all of this. This is now a bird's eye view to get you acquainted with the real world architecture, and then we understand how we can use these Google services and host this application on Google Cloud. Now we are just discussing a generic website and various components, various moving parts that put together a website, which is handling, say, more than 1 million customers by now. All right, so we have this CDN where we are storing our static files, metadata, media files, and so on. Well, now that this is sorted, we also have another part of our application. There can be a notification engine. For example, if you are having a website, say someone purchases something, you want to send a email notification or a push notification to his mobile phone that your purchase was successful, your order has been taken in, you will be receiving your product in the next X days. So these kind of communication notification pushes go in to the customers, and to send them across, we need some notification engines. Now, these kind of notifications do not have to be real time. They can go through a asynchronous messaging queue. So you have these pub sub notification servers, through which you can asynchronously queue up the messages or events and send them out. And not only for notification, you can use PubSub for many asynchronous parts of your workflow. For example, say someone creates his user and logs in, and then he subscribes to certain features in your service. Now, these events do not have to be done immediately, because they can be activated, say, 5 minutes later as well, and send a notification is sent to the user. So when we build an architecture, we try to make it as asynchronous as possible, so that the system can handle the load, and you can scale up your services. So when your events are going through a queue, you have time to stop that queue and even scale up your services. But when you're doing it real time, say for example, when your server is maxed out and you have a real-time request coming in, at that point the server would be unable to solve it or respond to that request, and you will get an error message. So handling the request asynchronously helps immensely to solve these kind of issues that comes out of synchronous messaging. Well, that is about synchronous workflows, asynchronous workflows, and how we do it using PubSub. And then we talked about push notifications, and we have different servers that subscribe to different queues and send the notifications out to users through other services like SMS sending services. There are SMS gateways, there are email gateways to send out emails. So that is another thing that is handled. Now, this architecture also has another aspect that is called analytics. Well, every business would have an analytics system where it will get in the real-time data and batch data and analyze it and understand different aspects of the business. For example, it will get clickstream data from different sensors, IoT devices, from the logs, and analyze it for business intelligence. For example, say you want to analyze how many users came into your website, how many users watched a particular page for a particular amount of time, how many users logged into the website and bought a few products, how many users clicked on products, moved it to the shopping cart, but did not purchase it in the end. So these kind of analytics help the business to plan ahead. Like you can know how many users are not being able to purchase, and then you can maybe try and probe the reason for that. For example, you can know like what is the most searched product in your website. So maybe you can stack up those products for future. So what is trending and all that. So business analytics help creating reports for the business. And for that, you need tools. Obviously, these have to work asynchronously and they have to stack in a large amount of data. So you would need warehousing for analyzing these data. You can put in machine learning algorithms in there, create certain models to predict about your business, and so on. So these are the various moving parts. Like one was where the real action is going on, the website, the database, the middleware of the application servers, you have the CDN for static content, you have the PubSub for asynchronous workflows, you have the notification engine for push notifications and emails, you have this data lake for different kinds of data to come in where you run your extract, transform, load processes, ETL, and then you run your business intelligence engine and you warehouse your data, make it meaningful, create reports, also ingest that data into machine learning models for predictions for the future. So that is one part. Another part I'm missing, that is about how do you handle the logs. That is also an aspect. So here you can even handle the logs by putting it into a log database such as Elasticsearch, and then you can use dashboards such as Kibana or Grafana to create metrics and view the logs. So that is what this architecture is about. Now we will discuss a bit about how we can deploy this architecture on Google Cloud. So if you are a startup like our shoppingcart.com, then it's possible that you have a very small team of developers who just would like to spend their time developing their applications and not much time administering. And say you do not have system administrators, or you don't have the bandwidth to have a DevOps system admin kind of a person in your team. So you would like to worry less about managing the servers. So you have options like Cloud Run, App Engine, where you just have to put in your application and everything else is taken care of. The environment is created. For example, if your website is on PHP, then you can spin up a PHP particular version that you need and then just put in your code in there and it runs. So Cloud Run, App Engine would be great. You can also, so you won't have to manage servers there. They're serverless and they can scale as your traffic grows. Cloud Run offers you to run serverless containers. So not just supporting the web traffic, but also WebSockets, gRPC, and so on. If you want to run containerized apps, but with more configuration and flexibility, then we can use Kubernetes. So if your app is containerized and you want to orchestrate it, you can use GKE for that. So I'm just talking about modernized way to bring your application into Google Cloud. You can just lift and shift and put it on a compute engine as well, on a virtual machine. But these are the various ways. So we are just having a discussion where we are discussing the various ways we can do the same thing. So just keep your options open. It's not that I'm asking you to do this, but these are the various options. If it's a container, you can use GKE. If it's if you want, you can put it on serverless. You can put it on Cloud Run, App Engine as well. Now, if you just want to lift and shift, and you can also use the virtual machine option as well. I'll come to that in a bit. But if we are using Kubernetes and we do not know much about Kubernetes, then using GKE is pretty easy because the learning curve is very flat and you have good control over your slave nodes that you have in your infrastructure. Google Kubernetes Engine also offers autopilot for when you need flexibility and control, and when you do not have Kubernetes experts in your team. So that is one option. And the final option is when you are going to, if you're not going to use either of this and just going to lift and shift your machine to VMs or virtual machines, then that can be done as well. So you have to select Google Compute, and you have to zero down on the amount of memory and CPU that is needed. And the disadvantages here are you will have to manage the OS upgrade patches and any other maintenance that is needed. So you have to do that yourself because this is not managed. The VM is managed by Google, but when you enter the VM, whatever you install and whatever applications that you use, including the operating system, has to be taken care by you. All right, so that's how you can move your application servers and your web servers. Say you can use any of these compute choices. And then once you have done that, you will need load balancers, as I said. So in cloud, you do not have these physical network load balancers that we have. Say in normal data center, we might use a Cisco or Juniper load balancer. But that is when we are doing it on a real infrastructure. on a on-premise infrastructure, but on cloud you have software-defined load balancers. Well, these load balancers are highly effective and can respond to millions of queries per second. So very, very highly efficient and scalable. Well, as I said, these cloud load balancers are highly powerful, and you can even use these load balancers to enable CDN options. So you can store or cache your static media in the nearest edge location. So the load balancer, instead of sending it back to the web server, sources the static content from your edge cache. So that's how the load on the web servers is reduced considerably, and the user has very good last mile performance. Now, for asynchronous messaging service, we would use PubSub and send messages to a topic, and then the service could subscribe to that topic and to receive those messages and send out those notifications and do other things that is needed for asynchronous workflows. So you can use PubSub from Google. And coming to databases, for relational databases, you can use Cloud SQL and Cloud Spanner. These are both managed databases. And for generic SQL needs, MySQL, Postgres, and SQL Server, for all these kind of needs, you can use Cloud SQL. Cloud Spanner is for massive scale relational databases that needs horizontal scaling. By massive, it means thousands of writes per second and tens of thousands of reads per second. So this is for like very, very special use cases. Like those of you who have used Amazon Web Services has a similar service called Redshift. So for huge size of data, you can use this. So that is about Cloud Spanner. But for most use cases, and in the use case that we are discussing, our shoppingcart.com, we would go with Cloud SQL. So that is the best relational database option available and very, very highly scalable. And for non-relational databases, there are three major options that are available in Google Cloud as we speak. So we have Bigtable, Memory Store, and Firestore. Now, Firestore is a serverless document database that can be used as a database as a service, which is easy to set up and provides fast results to complex queries in real time. I can liken it to MongoDB, and it also supports offline data and syncs, which makes it a great choice for mobile use cases along with web, IoT, and gaming. Now, there is another database, as I said, that's called the Bigtable. This is a white column NoSQL database that supports heavy reads and writes and has extremely low latency. And it's a perfect choice for events. You can liken it to Cassandra. So as we choose Cassandra database for events, and it's perfect choice for time series data. So data that is coming in from mobile devices, IoT devices, click streams. So this kind of stuff. And if your website has a recommendation engine, so recommendation event data is stored in Cassandra, and other personalization related use cases. And that is about Bigtable. Now you have Memory Store. Well, Memory Store is a fully managed in-memory data storage service for Redis and Memcached at Google Cloud. So it's just, you can say it's Redis or Memcached, which can cache your queries and responses. All right, so it is for transient data stores, temporary for making your database responses faster. And also it automates complex tasks of provisioning, replication, failover, patching, and all that. So it's great for speed of your website, for gaming, for leaderboards, chats, and so on. So that is another thing that we use. Now we'll discuss a bit about how we do the analytics thing at Google Cloud. So what are the various analytics tools? As we discussed, we can ingest the batch data from cloud storage and real-time data from applications using the asynchronous queue, the PubSub, and using that messaging service, we can scale to ingest millions of events per second. Data flow is another service that can be used for processing and enriching batch and streaming data. So it is based on Apache Beam. So you can use data prep instead for processing if you're looking to do the transformations with the UI on a no-code fashion that can be done. And if you are using a Hadoop ecosystem, then there is a service called Dataproc that would be a better choice for processing. So it is managed in the Hadoop platform, Hadoop and Spark platform, and allows you to analyze the data faster instead of worrying about managing and standing up for your Hadoop cluster. This is about how the ETL part happens. Now for warehousing, BigQuery is a serverless data warehouse, and it supports SQL queries that can scale to petabytes of data. And it can also act as your long-term storage, and also you can build a data lake using BigQuery. So we'll talk about what a data lake is in coming days. Now, finally, we discuss about machine learning a bit. So with this data, we can also train our models, and or we can use pre-trained models to create recommendations. Say, for example, you have this shoppingcart.com, and you have a certain user who buys, say, electronic items, and another user, a new user, is also searching for electronic items on your website. So you would like to recommend certain things to that user. So how can we recommend random things to a user? We can do that by analyzing the behavioral patterns of the previous users who is interested on electronic items. So whatever kinds of tastes he have might be overlapping with this new user. So these kind of decisions can be made by machine learning model training and predictions. So to facilitate that, there are various kinds of AI-based services on Google Cloud. So one of them is Vertex AI, another is AutoML. So these kind of services support, have pre-trained models for common use cases, so you can reuse them. And then you can also build custom models using various frameworks like TensorFlow, PyTorch. So these are all available in Google Cloud. And finally, when it comes to security, we all know that security is a shared responsibility. We have to go hand in hand with the cloud provider as well as the customer. So we secure our data, Google secures the infrastructure. So that is how it works. So we'll come into that later. So for Google security, you have various tools that we use, and you have your various kinds of firewall mechanisms, heuristic scans, and all that. So there is a tool called Cloud Armor. So Cloud Armor first traverses the data and only when convinced and all the checks passed, then it is forwarded to the load balancer. The load balancer then sends the respective backend with middleware API gateways like APG. And then there are also different layers of security in the API gateways as well. And there is, in Google Cloud, you have a security command center where it checks different vulnerabilities and threats and reports you so that you know what is coming and whether you should add a rule for that and so on. Now, to make your deployments easier in the cloud, Google Cloud also provides a lot of tools that are based on DevOps practices. So you have tools like Cloud Deploy and Cloud Build, where you can build your code, package it, and then deploy it using all the good practices of GitOps deployment pipelines. So that is also taken care of, as well as Google Cloud has various monitoring tools. So your application is continuously monitored, logs are recorded, and so on. Now that we know about this shoppingcart.com and how it was deployed to Google Cloud and various Google Cloud services that were employed into hosting this website, let's now focus on the various categories of GCP services. So basically, you can break it down into 5 categories. So I table it this way because it helps me remember the Google Cloud services. There are many, many more. These are just the basic ones that you would need to get any infrastructure going. So there are 5 categories. You can club them as compute, storage databases, networking, big data, machine learning. So 5 categories. Under compute comes compute engine, app engine, container engine, cloud functions. Some of these are serverless, some of these are VMs, some of these are containers, but the purpose is to run your compute services. Then comes the databases. As we said, some are NoSQL, some are SQL, some are caching. So various databases under them are cloud storage, cloud SQL, cloud bigtable, cloud spanner, cloud data store, persistent disks, and data transfer. The later two are storage mechanisms, not databases. So you can now go through, now that you get an idea of what I'm talking about and what Google Cloud is, you can now look up all these and read the official docs and understand better. So I'm not going into what cloud storage is, what are its features, because all that literature is available online. So I'm just having a discussion with you just to explain what are the various things out there in Google Cloud, what they do, and how you would be using them. Well, going back to the third club is the networking club. Well, there you have various components, common being the virtual private cloud, cloud load balancers, cloud CDN, cloud interconnect, and cloud DN. And then we have the analytics wing, or the big data, as well as IoT services. So the important ones being BigQuery, we spoke about it a while ago, Cloud Data Flow, Cloud Data Proc, Data Lab. We have the PubSub services, asynchronous messaging. We have Google Data Studio, we have Cloud IoT Core. And for machine learning, we have Cloud Machine Learning Engines on Google Cloud, Cloud Jobs API, Cloud NLP, Natural Language Processing, Cloud Speech API, Cloud Translation API, Cloud Vision API, Cloud Video Intelligence, and so on. We'll come deep into this in some of the upcoming lectures. So that is about a basic overview of Google Cloud Platform Services. Hope you like this session. If you have any questions, feel free to shoot it down in the comments, and we'll have many more exciting sessions, and we'll also invite some special guests in our upcoming session so that they can also share their experiences from Google Cloud. Thanks a lot.